All right, let's just jump right in. We're about to pull back the curtain on what can feel like one of the most intimidating, but also one of the most powerful skills for any developer on Windows: advanced debugging. And look, this isn't just about fixing the occasional crash. This is about truly understanding the deep, complex conversation that's happening between your code and the operating system itself. And that's really the big idea we're kicking off with. The source material for this whole explainer makes one thing crystal clear. This is not magic. It's not some dark art. It is a craft, it's a science, and it's a skill that you can learn. It's what separates just kind of struggling with bugs from methodically and confidently solving them. So to get there, we have to make a little mental shift. It is so easy to see the operating system as this impenetrable black box, right? It just does stuff and we hope for the best. But what if we started seeing it for what it really is? Yeah, it's an incredibly complex piece of code, for sure, but it was written by engineers just like us. It follows rules, it has a structure, and because of that, it can be understood. To get us there, here's our game plan. First, we are going to build out our essential toolkit. Then, we need to learn how to decode the system's own language. Once we've got that down, we'll be ready to go out and slay the 3 toughest kinds of bugs you'll ever face. And finally, we'll see how to learn from our mistakes by analyzing the aftermath. Okay, first things first, you gotta have the right tools for the job. You can't just wander into the depths of the operating system with the right gear, and that's exactly what we're covering right here. So the foundation, the cornerstone of this whole thing, is the Debugging Tools for Windows package. Inside, you get these super powerful console debuggers, but the real star of the show for most of us is going to be WinDB. That's the graphical debugger. And it also comes with some really cool proactive tools, like Application Verifier, which we'll get to in a sec. And this tool is a total game changer because it's proactive. See, most debuggers are for picking through the wreckage after a crash. Application Verifier is different. You run this thing during development. It's like a drill sergeant for your code, putting it through its paces to find those really nasty, hard-to-spot bugs like heap corruption or using an invalid handle, way before they have a chance to blow up in production. And you know what? Turning it on is actually surprisingly easy. You use this little tool called glags that comes with the package. You literally just point it at your app's executable file, and then you flip a few switches to turn on the checks you want, like page heap for memory problems, or the standard verifier tests. It's basically like telling Windows, hey, could you keep an extra close eye on this program for me? All right, so moving on. We've got our tools, but having a hammer doesn't make you a carpenter, right? Now we have to learn the language that the debugger speaks. Because without understanding these fundamentals, all the output you're going to see is just, well, it's just noise. And wow, this slide right here perfectly illustrates the most critical concept of all: symbols. On the left, that's what the debugger sees without them, just a bunch of random, meaningless memory addresses. But on the right, once you load the symbols, those PDB files, that same address is instantly translated into a human-readable function name. I mean, this is literally the difference between being completely lost in the woods and having a detailed map. And to manage all this, you're going to use a few key commands. /sim is how you tell the debugger where to find all your PDB files. LM lets you check which modules actually have their symbols loaded. But the real magic, the command that feels like a superpower, is DT. It stands for display type, and it lets you take a raw block of memory and tell the debugger, hey, interpret this as a specific data structure. It turns hexadecimal gibberish into organized, meaningful information. It's awesome. And as you're digging through all this system code, you start to notice these fascinating little details. For instance, a whole bunch of system functions start with this weird instruction: move EDI, EDI. At first glance, it looks like it does absolutely nothing. But it's not useless. It's actually this incredibly clever 2-byte placeholder. It allows Microsoft to patch a running system by replacing that instruction with a junk to new code, letting them fix critical bugs without forcing a reboot. It's a little secret of the OS, right there in plain sight. Now, to figure out where we are in the code, we have to talk about the call stack. The easiest way to think about it is like a stack of plates. Every time one function calls another one, a new plate gets put on top. And on that plate, you've got the arguments for the new function, the address of where to go back to when it's done, and all of its local variables. Following this stack of plates back down is how we play detective and figure out the exact path the code took to get to a crash. All right, we've got our tools, we speak the language, now it's time to go hunting.
In this section, we're going to take everything we've learned and apply it to conquer the 3 most common and, frankly, most difficult types of bugs a Windows developer will ever have to face. Think of them as the 3 dragons of debugging.
So let's talk about our first dragon, memory corruption. And this quote just nails why it's so tough. The actual bug, the moment your code writes to the wrong place in memory, and the crash that it eventually causes can be millions or even billions of instructions apart. You're almost never seeing the cause. You're just seeing the symptom way, way later. And that's what makes it so incredibly hard to track down. Now, this kind of corruption usually happens in 2 main places. You can have it on the stack, which is often caused by a buffer overflow that smashes the return address. Or you can have it on the heap from things like writing past the end of a block of memory you allocated or trying to use memory after you've already freed it. And for each of these, we have specific weapons. Application Verifier and its page heap feature are your absolute best friends for catching these errors the moment they happen.
Okay, on to our second dragon, the deadlock. Oh, you've all seen this. You click a button, you try to do something, and the application just stops. It freezes. The window goes white, you get the spinning cursor, it's not responding, it's just stuck. This is the classic, absolutely infuriating symptom of a synchronization bug.
So when you see that freeze, when everything just grinds to a halt, you need to simplify the problem. There is only one question you need to ask to solve the entire mystery. Who is waiting for whom? That's it. A deadlock is almost always a circular wait. Thread A is waiting for something thread B has, and at the same time, thread B is waiting for something thread A has. They're stuck. And here's exactly how you answer that question. First, you attach your debugger to the frozen process, and you just look at the call stocks for all the threads. You're looking for any threads that are stuck in a waiting state. Then, step 2, you inspect the lock they're waiting on using a command like /cs, and that will tell you who owns the lock, which leads you directly to the other thread in this deadly embrace. Problem solved.
And our third and final dragon, the dreaded access denied error. So debugging this is always a 2-part investigation. Part 1 is who is asking. You use the clip token command to look at the security token of the thread. Think of this as its security ID card. Part 2 is what are the rules. You use the clip² command on the object it's trying to get to, like a file, to see its security descriptor. That's the guest list. The solution to your problem is always going to be where the ID card and the guest list don't match up.
Okay, let's head into our final section here. So far, everything we've talked about has been live debugging, with the process running right in front of us. But what about all those crashes that happen on a customer's machine, halfway around the world? Well, that's where we learn from the aftermath. And the key to this entire world is the crash dump. A dump file is, and I love this analogy, it's a fossil. It's a perfect snapshot of your process, frozen in time at the exact moment of failure. It's got all the process memory, all the thread states. It has everything you need to investigate that crash as if you were sitting right there when it happened. And here's the best part. You don't even have to be there to get this data. Windows has these incredibly powerful automated systems built right in. For your customers out in the wild, Windows Error Reporting, or WRE, can collect these dumps for you automatically. And for your own servers, a tool like Debug gives you this amazing searchable control, letting you set up rules to generate dumps for specific kinds of crashes or hangs, or even just high CPU usage. So once you get one of those dump files and you load it up in WinDB, this right here is your magic wand. The command is xanalyze-v. It performs this incredibly sophisticated automated analysis of the entire crash. It'll identify the fault. It points you right to the failing thread and instruction. It often gives you a fantastic starting point for your investigation, saving you potentially hours of manual work. It is always the very first command you run.
So there we have it. We've gone from looking at the OS as a mysterious black box to seeing the intricate clockwork ticking away inside. We've seen the stack, we've seen the heap, security tokens, and all the tools that let us inspect every last gear. So the final thought I want to leave you with is this. Now that you've gotten a peek behind the curtain, how are you going to look at a piece of software, any piece of software, differently from now on?